There is a digital logic board in this game. It's one of the first early uses of digital logic circuitry in an arcade game. This is circa 1974. The logic board is located behind this display panel. This is the schematic for the logic board. A couple of things that are going on here in the schematic. So you have your coin switch up here. Normally it's closed, supplying voltage to charge up a capacitor, and then when you close the coin switch by a coin going through, it flips the switch to this position, dumps the charge in that capacitor through to turn on this transistor, and that transistor in turn pulls the trigger of the 555 timer to ground, and that sends out a pulse. This is configured as a monostable one-shot multi-vibrator. That's the digital logic term. And basically what it does is puts out one pulse per coin so that you can come over here and trigger this circuitry, and it's feeding over to here. All of this keeps track of what credits you have, how many credits, because you can put in multiple coins to get a credit, or put in a coin and get 2 plays. So that's kept track of over here on this side. Down here, the amount of time you get to play is determined by another 555, but this is configured as an astable multi-vibrator. In other words, a timer or a clock. And you've got resistance here in series, and you tap off of that, and the more resistance you give over to this pin, the slower this will time. So that's what increases or varies the length of the game. And then the output of this timer hits these step-up counters, and that goes over and controls the rest of the circuitry. On this side you have the time display. These are those 2 vacuum fluorescent digits that make up your time, and over here this is the other display, which is your score. We have some logic drivers that can drive the different segments, and it is being supplied with 185 volts, so there is a shock hazard back here in this area. You have to be careful. But the drivers are being given their signal by some counters here. These are digital logic counters that, as they get pulses, they count up and they convert from a digital code into 7-segment, so that they can show you 0 through 9 on each digit. Over here, tapped into your score circuitry, what's coming out on these pins is binary, and that is being tapped off and looked at by a series of AND gates. Over here you have an adjustment that as you're counting up, you will have a logic level on different ones of these pins, and you can pick which one you want to take off and go back. And if you do get a right number of hits, for example, this is set to 9, so at 9 hits this logic level will go high, and you would have a pulse sent to here, so that will extend the time, because this circuitry rolls around and goes back to keep this going. So you extend the time and get about double the length of time for play if you get the right number of hits. Down here is what's commonly referred to as a debounce circuitry. You have the contacts from the hit relay, the old electromechanical relay, and those contacts have mechanical bounce, and when a set of contacts goes to close, they don't just close completely and stay. They actually will bounce open and close as they're coming together. It's only a few bounces. It lasts milliseconds, but digital logic circuitry can react to that and see every one of those little bounces of the contact as a separate input pulse, and that would cause havoc with all your digital circuitry. So what this does is it's a set of NAND gates that feed back on each other, and the way this works is you have a forced logic level, either a 0 or a 1, always sitting here as the contacts are in one position. And then when you get a hit and the contacts energize and switch over to the other side, and then what happens is the very first time it contacts, it switches the logic level here, and it stays that way as it continues to bounce and settle out. And then when the relay de-energizes and it switches back, the very first contact it makes causes the logic level to go back to its original state. So this can bounce all it want, and this will just have a single 1 to 0 and 0 to 1 transition. It's a de-bounce circuit, and very common to have this when you're transitioning from electromechanical into a solid state circuitry. You also have a similar one over here, de-bounce, coming in off the credit switch. So when you push the button on the front panel to start a game, that's being de-bounced also and sending its logic level on. This set of NAND gates looks like this. You might think it's a de-bounce circuit to begin with, but it's not. It's just a simple latch or a flip-flop to hold level 1 or a 0. One side comes in and pulses it to set it. The other side comes in and pulses to reset it. So, look the same, but they serve a little different purpose. If you're going to work on digital circuitry like this, it's a good idea to have some data books. This is in my library. Data books from all different parts manufacturers, all the different companies like National and Motorola and Texas Instruments. And you get yourself a TTL transistor to transistor logic data book. Look up the part numbers. A 7490 and a 7493. They're both counters, and here in this data book you can see that 7490 is what's called a decade counter, whereas 7493 is a 4-bit binary counter. They both do the exact same thing, but a decade counter, decade meaning 10, it counts from 0 to 9. So that's exactly what you need to drive your display digits, because you're going to be doing the numbers 0 through 9. So this puts out a binary sequence, but it only counts from 0 to 9 before rolling over. And then this converts it from binary to the 7 segments. Where over here, the 7493, those are full binary counters. So you have 4 bits that are outputs, and in binary, 2 to the 4th power, you have 16 different combinations, or it can count from 0 to 15. All of that is explained in this data book, as well as logic tables. Here you can see that for the decade counter, you're counting from all lows to 1001, that's the last count, and to you and I in decimal, that's 0 to 9, then it rolls over. Whereas the 7493, it counts from all lows to all highs, so that's 0 to 15, which is 16 different count states. And then the rest of this tells you logically what's happening inside the chip. And you have all the specifications like how much voltage it can handle and current ratings, things like that.
For more information, visit GameRoomRepair.com.